So, one of the main uses for the polynomial long division is to help us find factors of high degree large polynomials. That way we can find the factors, we can find the roots, we can find the solutions, the x-intercepts, but it's a tedious process. And as always, people are looking for shortcuts. Two of those shortcuts are the remainder theorem and its corollary, the factor theorem. Corollary just means it's a special case of the factor theorem. Like a lot of special shortcuts, it's got its issues. It doesn't work for everybody. We have two restrictions right here. What they're telling us is that the factor that we're trying to divide by can only have two terms. Can't have divide by three terms. You can't be dividing by one term. You can only have two terms. And the leading coefficient on the first term can only be 1. So we can't be dividing by 2x minus 9. It can only be if the leading coefficient is 1. Now that leaves out a lot of possibilities. So it only works sometimes, but when it does work, it's very powerful. It says that if you're dividing, say, by x minus 3, then if you put a 3 into the polynomial, plug it in, substitute it, find out what a number you get, that number is going to be the same as the remainder is if you had done the division. So we're going to be able to find the remainders without actually dividing. Now you might think, who cares what the remainder is? Well, actually, we care more like what it isn't. If we're trying to factor, we don't want there to be a remainder. We want the remainder to be 0. And if we do this case, we're going to divide by a 2-term thing. Leading term has got a coefficient of 1. And we stick the number in the polynomial and it comes out to be 0. Well, values that make the polynomial come out to be 0, those are the roots, those are the zeros, those are the x-intercepts. So if this theorem can give us a short way to find out whether it's going to work or not without doing all the division, it will save us time. Please notice, though, that what we're dividing by is x minus a. What we put in the polynomial is just plain a. So if we're dividing by x minus 12, positive 12 is what goes in the polynomial. If we're dividing by x plus 3, negative 3 is what goes in the polynomial. And we've done this before with the factors. So if we had, for instance, x minus 3 times x plus 7 equals 0, then we knew that the only way this is going to work is if x equals positive 3 or x equals negative 7. So we're used to that kind of reversal of signs there. So let's check this remainder theorem out. See if it does what it says. These are problems we just did recently. So we'll look at each problem, see if we're allowed to use the remainder theorem, and if we are, then we'll go ahead and do it. So number 1, we're dividing by x minus 9. Does that fit the pattern? Well, yeah, it does. It said we're dividing by x minus a. But a negative 9 is not what we're going to put in the polynomial. What we're going to put in the polynomial is a positive 9. A is going to equal positive 9. So we'll substitute positive 9 anywhere we see an x. 9 squared minus 2 times 9, subtract 63. So we have 81 minus 18 minus 63. Well, that would be 63 minus 63. This comes out to be 0. which is good because when we did it with long division, the remainder came out to be 0. So this tells us the remainder is 0, which I'm not going to have room enough to put there. And that does tell us that this must be a factor. And a equals 9, or x equals 9, is going to be a root. Not only that, we know that the quotient is also a factor. How about number 2? Are we going to be allowed to use the remainder theorem here? If we have 2 terms, leading coefficient is 1, we should be able to. So yes, we can use the remainder theorem here. But it says a plus 3, we're not going to put in a plus 3, we're going to put in a negative 3 for a. Everywhere there's an a, we're going to replace it with negative 3. So negative 3 times negative 3 is positive 9. Positive 4 times negative 3 is negative 12, plus 8. So we got negative 3 plus 8, and that comes out to 5. According to the remainder theorem, that means if we did the division, the remainder should come out to be 5. Sure enough, when we did the division, the remainder came out to be 5. This theorem really does work. Tells us that this thing is not a factor. Don't worry about it. Which, if we had done the factor theorem first, we wouldn't have had to have done the division. How about number 3? Got 2 terms. Shall we just stick a 1 in here? No, we can't. Because for this theorem to work, we have to be dividing by 2 terms with a leading coefficient of 1. We don't. We have a 2. Now, it is possible to get around it. We could divide this by 2, so we'd have a 1 in. But you'd have to divide this by 2, and you'd have to divide this by 2, and divide this by 2, and divide this by 2, and suddenly it's not a shortcut anymore. So this is not in the proper form to apply the remainder theorem. So we'll just move on to the last one. We're dividing by k minus 4. 2 terms, leading coefficient is 1. We can use the remainder theorem. But we're not going to put a negative 4 in here. We're going to put a positive 4 in here. The a that we put in the polynomial is going to be positive 4. Now, when we did the long division, we had to fake in an extra. There was no k squared term in here, so we had to put in a 0k squared. When we're using the remainder theorem, we're just going to stick a 4 anywhere there's a k. So we'd have 4 to the third minus 6 times 4 plus 1. Well, 4 times 4 times another 4 is 64 minus 24 plus 1. So that gives us 40 plus 1. According to the remainder theorem, that means if we did the division, the answer's going to have a remainder of 41, which it did. If what we were after was just whether or not this is a factor, this would have saved us time. We wouldn't have had to have done all the division to find out that it isn't a factor. Now, if we're doing calculus where we don't care about the factors in the problem, we would go ahead and do the long division. Right now, I'm going to ask you to please go ahead and do the practice for this